Hello, everybody. It is finally the time for the last video in our sequence of how a sun-like star dies. We've gone through the post-main sequence evolution all the way up through the asymptotic giant branch, where we saw that our star is shedding its outer layers, casting them back out into the ISM. It has fused up to carbon and oxygen in its core. So as it's going through this phase, it's infusing the interstellar medium with helium, carbon, and oxygen. It has enriched the ISM with helium and metals. But our star is not dead yet. It still has a little bit of work to do, and we still need to see where it ends up in our stellar graveyard. We will go through these last two phases of a sun-like star's evolution towards death, and we will take a look at one of the most photogenic of all the objects in the universe, the so-called Planetary Nebula. That is the last sort of gasps of our star before it turns into a dead white dwarf star. All right, so here is our Planetary Nebula, a misnomer. If there ever was one, it has nothing to do with planets, although whenever astronomers were originally observing these things, they were sort of extended whenever you look at them in the telescope. They weren't just a single point of light. The only other thing that really happens like that in telescopes are planets. So they wondered what these were, and they end up having a name since they look sort of planet-like in the telescope, or at least a low resolution, low magnification telescope. Hence, they recognized they were nebulae, so they called them planetary nebula or nebulae. This right here is the Helix Nebula. I'm gonna have plenty of images of these amazing celestial objects. Let's get to work. We have been going through these stages of stellar evolution for a sun-like star. Sun-like means a one solar mass star. We have gone all the way through, and we're at the last phases. We're going to go through 5, 6, and 7. These all happen rapidly over the course of tens of thousands to maybe 100,000 years to transition all the way from 5 down to number 7. So we're going to talk about both the planetary nebula stage and the white dwarf stage in this video. All right, so just going to put that up there since the animation didn't work fully. We are at the very end, or picture us at the very end of the asymptotic giant branch, the AGB. So this is whenever the star was going through those pulsations, and it was shedding the outer layers of the envelope, injecting them into the ISM. And with each iteration, with each pulsation, more and more of the outer envelope of the star is lost and injected into the interstellar medium. And it's slowly exposing the deeper, hotter inner layers of the star until essentially you're going to expose just the core layer, which is now going to be nearly a pure carbon oxygen mass, carbon and oxygen that can't fuse into a heavier material. And that is just going to be exposed to space. So with each pulsation, it's shedding more and more of its outer layers. How much mass is going to be lost in this process? If you start with a star like the sun with one solar mass, by the time it gets to the end of the asymptotic giant branch, typically it'll have lost half of its mass. Now, it lost some along the red giant branch as well, but the majority of the loss is coming here in the asymptotic giant branch. So the asymptotic giant branch phase ends when essentially the star has shed its envelope and it's done all the fusion that it possibly can, just leaving this carbon oxygen fusion ash core. And without any fusion going on in it, it's not producing the thermal pressure required to fight off the gravity that's trying to pull it together. So it's going to keep getting squeezed together tighter and tighter and tighter, a more and more dense electron degenerate core. And as it does so, it's going to continue to warm up. The surface of this thing is going to get hotter and hotter and hotter. The core is extraordinarily hot, but the surface is relatively cooler. And as it's now getting exposed to space and contracting, the surface will eventually hit temperatures upwards of about 100,000 Kelvin. That is extraordinarily hot for the surface of a star, except there's no fusion going on in it, so it's not really a star. But this is now hot enough where it's going to be emitting lots and lots of ultraviolet radiation. Plug this into Wien's law to convince yourself that the peak of the black body radiation would be very short wavelengths in ionizing ultraviolet light. And the great thing about ultraviolet light is it easily excites electrons. It ionizes pretty much any atom that's out there, especially the high energy ones. We call UV radiation ionizing radiation. So now we have this flood of ultraviolet radiation that's screaming out into space at the speed of light, where it's going to encounter those expelled shells of gas that used to be the envelope of the star. Get all those electrons super excited, rip them off of their atoms, and then you have those electrons that are getting back together with the atoms, and they cascade back down towards the ground state. While they do that, they're emitting photons. Lots of those photons are going to be invisible light. Remember that whenever you jump to a higher energy level, and then you cascade down through several different energy levels, emitting several photons. We call this process fluorescence. So uh, we are now going to see all of these expelled shells fluorescing, giving off light. They're being fluoresced by the dead remnant core of the star, which is going to create a absolutely fantastic object that we call the Planetary Nebula. And you can think about it as a star, and I'm going to use star in quotes because it doesn't have any fusion going on, but it's easiest to just keep referring it to as a star, just like we refer to a white dwarf as a white dwarf star or a neutron star as a neutron star, even though they don't have fusion going on in them. But we can think about the Planetary Nebula as a star in two parts. It's a celestial object that has two different parts. It has the remnant carbon and oxygen core, which you can see here. So this is a planetary nebula, has the oh so wonderful name of ESO 378-1. I'm sure somebody will give it a better name at some point. So here you can see the carbon oxygen ash core that is super duper hot, so it glows pretty brightly despite being really, really, really small. So it's glowing really, really brightly, giving off plenty of ultraviolet radiation to hit those expelled shells of gas, causing them to fluoresce and glow, giving us these absolutely stunning objects. So the two parts are the exposed carbon and oxygen core of the star that is on its way to becoming a white dwarf, and then our expanding shells of expelled gas that are now fluorescing due to the ultraviolet radiation given off by the remnant core. Now, this is just a idealized view of what a planetary nebula looks like, because we think about the pulsations of the asymptotic giant branch, and it's easiest to picture everything symmetric. So whenever it expands outward, it'll send out a spherical shell of gas, which rarely, but sometimes, yeah, it goes out as a nice spherical shell. If you consider the rotation, the magnetic fields of the star, the fact there might be planets in orbit around it, it's rare that you get a nice symmetric shell going out. So often planetary nebulae don't look like these nice idealized bubble views that we might have of what you would think they'd look like. Here's another sort of nice idealized bubble view, but you can start to see there is a little bit of asymmetry going on in it. Well, here's our core remnant star right here. So this planetary nebula, and what we're going to do is we're going to look at lots of pictures of planetary nebula because they're just stunning celestial objects. This is called Abell 7. And here we have our remnant core sitting right at the center, and you can see the expelled layers that used to be the envelope of the star that are fluorescing now. Has some denser parts and it has some thinner parts, but it still mostly looks like a bubble. Let's take a large gallery view. And this is what planetary nebulae look like. This is just a small subsample of all the ones that we've observed, but it gives you an idea that these things have some pretty complex geometries. These nice little, oh, it looks like a bubble in outer space like you'd expect. Those are the rare ones. Most of them, due to asymmetric winds, binary companions, possibly orbiting planets, because we know planets are pretty common now. All sorts of different things make it so those expelled shells of gas are not spherically symmetric. They are complex. And I have a quibble with this image that I didn't notice before. This one is not a planetary nebula. That is the Crab Nebula. That is a supernova remnant. But the rest of these are planetary nebulae. and they have quite asymmetric shapes. In fact, why don't we go ahead and take a look to enjoy some of these objects. So one of the more famous planetary nebulae out there, the Helix Nebula. Here we can see the remnant core, and then we can see the glowing shells of gas. And you'll get all sorts of different colors depending on the temperature, the level of ionization, what elements are there, and you'll get all these complicated shapes. You end up actually having these really, really interesting things where this inner part looks, you'll always have like sort of this clear but different glowing inner part of the uh, planetary nebula. And that's because whenever that initial shock wave goes out, it reverberates, comes back, and sort of superheats that area. And that's why you can see it kind of blows out a little bubble, and you can see all this complex structure in the dust from the two different sort of parts of the expelled part of the planetary nebula. So the Helix Nebula, one of the most famous ones, easy to get a picture of with a small telescope. If you ever have access to the physics rooftop here at the University of Tennessee, I encourage you to go up to the rooftop. This is a common object we show. It does not look like this in a telescope, but even I have just used one of the telescopes without even planning my trip or trying very hard. I just hooked my camera up to a telescope and I got a pretty good picture of the Dumbbell Nebula. Nothing like what's being taken with one of the best telescopes in the world, the VLT, which is where this image is from. But again, you can see the green is from glowing oxygen, and you can see some hydrogen as well. And there's our dead remnant star. Another one, NGC 2899. Almost looks like a glowing cosmic butterfly. Although we'll get to the Bug Nebula, which really looks like a butterfly. The Retina Nebula, which before these high resolution images, you can still see why it ended up being called the Retina Nebula. You can see all these dark dust lanes that are going through the central region. With a little bit lower resolution, if you ever look at an eye up close, you can see that it has that weird pattern of coloring, the light dark flecking and specks. So the people thought that this looked like a retina. And then you can see that this one is relatively symmetric, but not spherical. The Saturn Nebula, because it kind of looks like Saturn in shape, where you got a central blob and then things that are jutting out that looks kind of like the rings if you were looking at a very, very blurry image of Saturn. But here you can see all the different parts of a planetary nebula, the remnant core, that weird inner part where the shock wave went out and reverberated back, and therefore created this super hot bubble in the center part, and then the outer parts of the bubble. The glowing fluorescent gas that used to be the envelope of our asymptotic giant branch star. And the cosmic butterfly itself, or just the cosmic bug. So let's go with moth, since I already said butterfly. Here we have the Bug Nebula. I have lots of images of planetary nebulae in the unit slides as well, but I intentionally chose different images so you can look at those on your own. And here in the video, I gave you a set of different images. The only ones that overlap are the Bug Nebula, but the image that I'm giving you in the unit slides is a different picture taken with a different telescope. Oh, and I forgot that I had one more just to show all the cool kind of stuff that we can do with this. So here is the Cat's Eye Nebula, 3 different views. So one is a very early view in 1994 with the Hubble Space Telescope, where you can see the expanding shells of gas, and you have all these different shells, and how they overlap from our point of view ends up giving it this really, really cool structure. You can probably see why they call it the cat's eye, because it kind of looks like a cat's eye. This is a more modern view from the Hubble Space Telescope, where they're choosing how to do the coloration based on what filters that they're using and what usually elements those filters are isolating. So, for example, the one on the right, this one is showing where they have selected different filters to put on the camera that only let in certain wavelengths of light. And these are very narrow band filters that let in very specific wavelengths of light. And they had a filter that was attuned to detect a oxygen emission line, one that was there to detect a nitrogen emission line, and another one that is tuned to detect a oxygen emission line. And then that way they could take a picture of where all the hydrogen is, take a picture of where all the nitrogen is, take a picture of where all the oxygen is, color them. So just say that, let's make the hydrogen picture red, the nitrogen picture green, the oxygen picture blue, overlay all three of the images to make a composite image. And now you can see where the different elements are hanging out in this planetary nebula. So these are elements: hydrogen, nitrogen, oxygen. The nitrogen, oxygen being produced during the life of the star that are now getting injected out into the planetary, or back into the interstellar medium. All right, so the planetary nebula, that phase is tragically short, lasting less than 100,000 years or so for a sun-like star. Uh, but they are ephemeral yet beautiful. What happens at the end? Why don't those endure? Well, after several tens of thousands, maybe 100,000 years or so, to remember that those shells of gas are still expanding. They're going out into pretty much the vacuum of space, so there's nothing really slowing them down. And they're moving at tens of kilometers per second. So give it enough time, and those shells of gas will expand away. And what's happening with our core? Well, it's just sitting there now with no fusion providing new energy going into it. So it's slowly cooling down. The shells of gas are getting further away. And each one of those individually makes it so it's harder for those expelled shells of gas to fluoresce. The cooler remnant core means that you have less ultraviolet radiation. Less ultraviolet radiation means less fluorescence because you're not moving those electrons around as vigorously. The shells of gas being farther away, well, energy decreases in an inverse squared law. The brightness of the ultraviolet light decreases as an inverse squared law. So as those things get farther away, they're receiving less energy from the core, the remnant core as well. So eventually the gas will get too far away where it can no longer be significantly ionized. And you can also think of it, the gas is cooled down to a point where it's no longer ionized. And if it's not glowing, guess what? We can't really see it. It's just a thin gas in outer space. So it'll stop glowing and we can't see it anymore. All that material is going back out into the ISM where it can join up and become part of another nebula and maybe form a molecular cloud and become a new round of star formation. So what do we have left? We just have our carbon and oxygen remnant core that's now visible to space as its own celestial object. What does this remnant core look like? Well, it's mostly carbon with some of that oxygen mixed in as well. And then it's shrunk. How it contains about, if it was a one solar mass star, it's now about half the mass of the sun. It could be upwards to retaining most of the mass, or what started out as a slightly larger than a one solar mass star. It could be up to about a solar mass or so. But let's just go with half the mass of the sun. And it's only about the size of the Earth, a radius of 100 times smaller. That is tiny. These are really, really small objects, but it still has an incredible amount of mass, about 10 to the 30th kilograms of mass. And what is preventing this thing from collapsing? So what makes it so, what counteracts the gravity that's trying to crush it? This electron degeneracy pressure. So it's held together against gravity by electron degeneracy pressure. It's super hot, initial temperature of about 100 K, but then it's just going to be cooling down. It's only shining from its stored heat, and it's extremely small. So these things are quite dim. Despite having a really, really high temperature, they're really, really, really small, about the size of the Earth, so they're quite dim. But they're glowing white hot, and they're the size of the Earth, containing about half the mass of the sun. In fact, maybe it's best to talk about this in terms of what would the density of this, now what we call a white dwarf. It's really, really small and really, really hot. It's about the size of the Earth with half the mass of the sun. A teaspoon of white dwarf material would weigh several tons here in Earth's gravitational field. If we could have white dwarf material and I could set it here on this table, no, it would crush this table. It would be several tons of material, just a teaspoonful. A incredibly dense object. And now, there it is. We have completed the stellar evolution how a star leaves the main sequence, a sun-like star leaves the main sequence and dies as a white dwarf. We have seen our sun start as a G2 main sequence star and go through all of the stages to end up as a white dwarf that has a very high surface temperature. Some of them are way over here. Very, very high surface temperature, and they're incredibly small. And it's really technically the dead remnant core of the sun-like star, made out of carbon and oxygen. And since it's made out of carbon and oxygen, we call those types of white dwarfs the kind of white dwarfs formed by sun-like stars, carbon oxygen white dwarfs. There are other types of white dwarfs. I decided not to include those in the video. That's something you can go study in the unit slides on your own. Yes, you will be responsible for that material. But there's just so much to cover in this. I didn't want to berate you with hours of videos. So we'll leave this by introducing the carbon oxygen white dwarf is the type of white dwarf that's formed by the death of the sun. So in roughly 5.5 billion years, our sun will leave, well, about 5 billion years, it's going to leave the main sequence, go from 1 to 2 on the subgiant branch, and then go from 2 to 3, ascend up the red giant branch, a total amount of time of somewhere less than 1 billion years or so. At the top of the red giant branch, it will experience the helium flash, which will move it down to the horizontal branch, where now we'll be fusing helium in its core, surrounded by a hydrogen burning shell. And then it'll develop a carbon oxygen ash core, have a helium burning shell, a hydrogen burning shell around that, ascend the asymptotic giant branch, which has those stellar oscillations with pulsations that shed the outer layers, causing it to become a planetary nebula. And then eventually it won't be able to ionize all the expelled shells of gas from the envelope, and it'll die as a white dwarf. And thus we have our dead sun as a white dwarf. In roughly 5 to 6 billion years, our sun will be a white dwarf, a carbon oxygen white dwarf. And at that point, we would refer to our sun as the progenitor star of that white dwarf. So whenever we talk about dead objects, dead celestial objects, dead stars, so white dwarfs, black holes, neutron stars, stellar mass black holes, the star that created them, or the star that they came from, we refer to as a progenitor star. And here we have finally filled out this entire table. And you can see there's a rhyme and a reason now. You start with hydrogen burning in the core until you build a helium ash core up. But then you still have the hydrogen burning, but now as a shell. Eventually things become hot enough. You hit the 10 or the 100 million Kelvin to fuse helium into something heavier. So it's no longer an ash core. It's a helium fusing to carbon and oxygen. So it's a helium burning core surrounded by a hydrogen burning shell. But this new helium burning is going to generate its own ash core eventually, and it's going to be a carbon oxygen ash core. But you still have helium fusion, so you have a helium shell burning around that and hydrogen shell burning around that. And that's the death of a low mass star because it never has enough mass to turn the carbon oxygen ash core into a new round of fusion to keep and sustain the star. So our sun-like star goes through its death throes, which are a planetary nebula, which ends in a white dwarf. And there we have it, the evolution of a sun-like star. We made it. I hope you've enjoyed this sequence of videos. I encourage you to rewatch them as many times as you need to really let this material sink in. And we will begin talking about the other really exciting parts about stellar evolution, how we can actually see this, how we can determine that this model that I just gave you is right, is true, actually occurs. We'll observe all the stages in nature or in the universe. We'll talk about weird ways that stars evolve because a lot of stars are in binary systems. So we still have to cover that. And we have to talk about how stars of different masses evolve, especially the high mass stars, which don't have a planetary nebula phase. They have enough mass to kick off another round of fusion, several rounds of fusion, in fact, where they can fuse carbon and oxygen into heavier elements like neon and sodium and a plethora of other elements. And we'll follow what happens until the logical end where fusion stops. And that happens, when that occurs, we have something extraordinary occur, a supernova explosion. All that to come. Stay tuned for those videos.